value for ideal case or at a constant value IC sat. Again, the ideal case respectively, where the transistor can be used as a switching device. And since this chapter is dedicated for how to design a transistor to act as a switch, uh, then only we have to take care of the cutoff region as well as the saturation region. We will start again with the same generalized circuitry. The same generalized circuitry which we had discussed in the last class as well as in today's last slide, where the output is nothing but can be taken as the drop between the collector and emitter terminals. B is the input, which is, or it is a common base circuitry. So base is the controlling one, emitter is the input, collector is the output. So output versus input, whatever drop is coming, that will be governed as tentatively the output. That is the voltage between the emitter and collector terminals. And Vi is assumed to be the arbitrary input signal, arbitrary AC input signal usually. For a given set of values of IB, as we know, IC equals to HFE IB and IE equals to IC plus IB. That means HFE plus 1 IB. You can neglect 1 because HFE value is very high. So you can write, we usually write it IE also HFE IB. The output can be obtained by applying the KVL in the collector emitter loop. That means V0 or the VCE is nothing but VCC minus IB into HFE, whatever current is flowing, because IE is HFE into IB into HFE, RE plus RC, assuming the similar current is flowing are through the emitter and the collector resistance. So what will be actually our design purpose in that case? Remember what we have calculated in the last class, or what we have estimated. First, there was cutoff region, then there was active region, because active region always comes in between the cutoff and saturation region. So if anyone can ask you, you have to design a switch, you can say very carefully, yeah, very fine, we can operate the transistor in the cutoff and we can operate the transistor in the saturation to make it off and on respectively. Yes, that is true, but the design challenge is something more different. When you're operating, suppose a simple switch of your light, tube light or fan in your home, what do you want? Your light should be on and your light should be off directly. That means when you have to operate a transistor as a switch, first it should be off and then it should be directly on. You do not expect your tube light or your any light or your fan should be gradually bypassing the active region. That means gradually increasing its emitting light and then show its full brightness. Never. You want, whenever you put your switch on, it should glow with your full brightness, with the full brightness of the bulb. That means you have to bypass the active region of the transistor, because the same transistor, whatever has been brought from the market, it possesses all kinds of operation. If you want to make it a amplifier in the active region that can act as an amplifier, the same transistor can act as a switch. So the carefully the design has to be made. You have to properly bypass the active region and you have to oscillate your operation directly, direct transition from off to on or vice versa. So that is the secondary challenge, and rather than that is the most crucial challenge whenever you are making a transistor as a switch. So we will try to first design the basic conditions for an ideal switch, then we will come the non-ideal conditions, what happens in the non-ideal conditions, and then we will come to the specific design rules, what kind of a resistance we have to choose, what amount of Vi or the input voltage we have to choose, so that we can come up with a perfect switch. सुप्रीत सिंह, मैं आपको बता के रख रहा हूँ, मेरे यहाँ पे आज थोड़ा इंटरनेट कनेक्शन का दिक्कत है, So if somehow I lost connection, क्योंकि मैं slide देख के पढ़ा रहा हूँ, मुझे Google Classroom का मुझे दिखाई नहीं दे रहा है. If somehow I lost the connection, just give me a call. Fine? Fine. तुम नहीं तो मुझे ध्यान नहीं रहेगा, मैं बकता ही रहूंगा और आप लोग सुन नहीं पाएंगे. So that is, we have to transfer the on and off bypassing the active region. So let's start. Oh, that's why we have to go for case by case analysis. That means the cutoff region analysis as well as the saturation region analysis. First one, the cutoff condition. IB is determined by the arbitrary input, obviously, because arbitrary input can be any input we do not know depending on the applications. As we know, for the choosing of the modes of operation from our last couple of classes, input voltage must be less than 0 so that the base emitter junction reverse bias to be ensured. And that will also definitely lose if ensure, because if Vi is less than 0, your IB, the base current, input base current will also be 0, because that will only ensure the cutoff condition. Vi less than 0, obviously not less than the breakdown voltage. That is the necessary sufficient condition. So if you can take the same equation, that is equation 1, which we have derived here after applying the KVL, and if we apply the same condition, that means IB equals to 0, then we will get from the equation 1, V0 equals to VCE is nothing but your VCC for Vi less than or equals to 0. So see what a beautiful condition is. If your Vi is equals to 0, there is no current flowing, IB equals to 0, that means what? Your IC is also equals to 0, but a full voltage VCC is appearing at the output. That is possible when it can be possible if you have a finite value of the resistor. So the entire bias voltage VCC will appear between the collector and emitter terminals, but eventually IC and I equals to 0 because IB equals to 0. So it is observed zero current flows at the output emitter collector circuit despite a finite and significant voltage VCC is appearing to the collector circuit. This is only possible if the impedance between the collector and emitter terminal is finite, which is the most important condition. That is, emitter and collector terminals can be equivalently viewed as an open circuit switch under the cutoff condition. The switch is open. Well, the VCC is flowing. The VCC can directly appear here at the output, but eventually no current is flowing since the switch is open. That is a equivalent representation of the switch when it is the case 1. That is the cutoff condition. Let's ideal, of course. Whenever we are taking Vi less than or equals to 0, that may be minus infinity as well, but we can't achieve, so that's why this is ideal condition. We will come into the non-ideal condition maybe in the next class. Case 2, saturation region, the other extreme one. Here IC reaches its maximum saturated value, IC sat. So for simplicity, let's assume both base emitter and collector base junctions have zero cut-in voltage. Otherwise, whatever equation, the KVL equation, you always have to add certain kind of a V gamma. Don't make the life complicated, since we are now considering only the ideal condition. They have, assuming they have zero cut-in voltages. So for saturation region, both the junctions have to be forward biased. So VCE or V naught should be equals to 0 in the ideal case, because V0 or VC equals to 0 can be created by increasing the VE in term of the increasing the value of the IB. Hence, from the equation 1 IB, we can directly land up with the equation 2 if we can substitute V naught equals to VC equals to 0, IB equals to VCC by HFE into RE plus RC. So output is 0, exactly the opposite case. Case 2 is of the case 1. The output is 0, but there is a finite value of the current is flowing. Previously, current was 0, but finite value of the voltage is appearing. Here it is exactly opposite. That implies the short circuited condition between the collector and emitter terminals, that is transistor will behave as a closed switch at the saturation region. The switch is closed and hence a proper current path is appearing, which is going into the ground, and that's why you can say the output is actually zero. So under ideal switching condition, IE equals to IC, similar kind of current is flowing. If we can take it as an ideal switch, no drop is occurring, so that's why I equals to IC, HFE IB. IB we have already calculated from equation 2, VCC by RC plus RE, which is the ideal saturation currents. So ideal saturation is the ideal saturation current for V naught equals to VC equals to 0 and IE equals to IC. Again, the ideal condition, never output gets 0 actually, and IE cannot be IC because here is a transistor, the effect of the resistance, there are many parasitic effects are also there, so IE cannot become equal to the IC in a non-ideal situation. Fine, so we will come into the non-ideal situation only today. Same cases we will try to interpret in case of a non-ideal situation as well. What is a non-ideal situation? In practice, the base emitter and collector base junction of a transistor has finite values of the cut-in voltages. So what assumption we had taken? The wrong assumption that we have to first counter effect. And VCE is also a VCE SAT. So you can't say always for every transistor which you have brought from the market, there is a saturation value of the VCE SAT. It can go beyond that. So it has a small but finite value in the saturation region of the transistor. So now the common emitter side under saturation region can be represented by the following equivalent circuit, where a voltage source VCE SAT is connected in series with an ideally closed switch. Similarly, non-ideal situation, because cutoff condition, there is not much of non-ideal situation. Only you have to take care of the breakdown voltages. But in case of a saturation region, that is when the switch is on, you have to consider the closed switch as well as a separate voltage source, assuming whose value is actually the VCE SAT. That compromise we have to make for a non-ideal situation. So using IE almost equals to IC and applying the saturation condition, that means V naught now is less than or equals to VC SAT, never be equals to 0. At the onset of saturation, we obtain IB, that is a minimum base current, is VCC minus VCE SAT by HFE into RC plus RE, or IC SAT by HFE. You just plug it from the equation 1, the initial equation 1, and substitute these conditions, you will get to receive the same minimum value of the IV, which is a modified equation from the ideal equation which we have carried out in case of equation 2. So equation 4 is a modified version of the, or ideal version of the equation 2, sorry, non-ideal version of the equation 2. So where IB minimum is basically the minimum base current required to drive the transistor under the saturation condition. So this is the one design aspect when we are considering the non-ideal situation, that is the IB minimum, what we have to take care while we are designing a transistor as a switch. Very fine. So that is the base current. But to be very honest, the minimum value of the base current can only is little bit beyond of our control, because बाहर से हम current actually control नहीं कर पाते. What we control the external voltage sources, that we are able to control that. So basically the first controlling parameter or the main controlling parameter is your VI. Whatever the external AC input signal you are applying, that should be first taken care of, or that's design should be first taken care of. So that is first primitive parameter, determination of VI, determination on VI, whatever. It is important to mention when a transistor is used as a switch, it is required to drive the transistor into the cutoff and saturation region in an alternative manner without driving it into the active region. So the choice of V is very crucial. You have to jump from one state to another state. This, sorry, this, just a minute. Just a minute, let's get it saved. Yeah. Sorry, come back. So case 2, saturation region, all words have been gone. Great. So here we are, the determination of the VI. So it is important to mention that when transistor is used as a switch, it is required to drive the transistor into cutoff and saturation regions in alternative manner without driving into the active region. This means the VI should be of two voltage levels. Either it should be of low voltage level, that is less than or equals to 0, or it should be high voltage level, some value of the V minimum. So that means 0 और V minimum के बीच में the active region is lying. So we can either make it 0 or we can make it greater than the V minimum value to make the transistor in the saturation region, where V minimum is the minimum voltage required to make the IB equals to IB minimum, because at the IC sat, the IB should be at the IB minimum value. If we apply the Kirchhoff's voltage law in the input circuitry, the same generalized transistor circuitry, now we are applying input loop, output loop, separately the KVL with IB equals to IB minimum, where VI equals to VI minimum. So we can write VI minimum equals to IB minimum into RB, IC sat into RE, since we are driving the transistor in the saturation region, plus VBE sat. Never forget there is a base to emitter voltage is also there. We are applying at the input circuitry, that is also correspondingly VC sat, whatever the voltage drop, because VC sat is a constant value. There is also a constant base to emitter or nearly constant base to emitter voltage drop should be there, which is we are defining as VBE sat, where IE almost equals to IC sat equals to IB minimum into HFE. पहले हम active region में क्या कर रहे थे, IC equals to HFE IB, now it is IC sat equals to IB minimum of HFE. Replacing the VI minimum with VI just to save the writing of energy, IB minimum equals to IB. We can write IC sat equals to IB minimum of HFE, and using the condition, now it cannot be equal. So IB greater than or equals to IC set by IHFE. In equation 5, we can obtain the VI, or the determination of the VI. If we just solve it in the similar manner, VI minus VB sat by RB plus HFE into RE greater than or equals to IC sat by HFE, that is equals to IB minimum. Or in other alternative words, VI greater than or equals to IC sat into RB by HFE plus IC sat into RE plus VB sat is the IB minimum into RB plus HFE into RE plus VB sat, which is the VI minimum, which gives you the minimum condition of the determination that required the condition to be satisfied by VI for the transistor to be operated in the saturation region. So whenever you are acting or you are making a transistor to act as a switch, if you have to make the transistor or the switch off, we know VI should be less than or equals to 0, but should not be much less than or equals to its cutoff region. Very fine. Or usually you can write it Vi less than or equals to VBE. But when you have to make the transistor on, you have to operate your Vi, or Vi should be greater than or equals to of your Vi minimum value directly, because in between any value you can put up, your transistor will go to the active region and it will start get amplifying before getting into the saturation region. So it will stuck into that linear region in the output characteristics. So you have to avoid this active region. Either you have to make it in the 0, or you have to directly jump to the transition to the saturation region. That is a portion of the determination of the VI, one of the crucial condition that you have to make. That is one aspect, how we can the input voltage. There are other design rules as well when you have to consider the transistor as a switch. One important part is that, I'm sorry, I haven't drawn it electronically. When your IB, the base current, is IB minimum, then you are designing it for the saturation region. Fine. What value of the RB it should be now in the to make it in the saturation region? Anyone, if I should be of certain minimum value to make into the saturation region, what should be your RB value, or the base resistance which is guiding your IB minimum to ensure minimum current? Anyone, to ensure the minimum current, the resistance should be
VI upon IB minimum.
VI upon IB minimum नहीं है, ठीक है, because that is complicated to find. RB should be RB maximum, certain maximum value. So while you are choosing your VI to be VI minimum to operate the transistor on, your corresponding design for the resistance to be chosen as maximum value. Then only you can ensure the IB minimum. Again, simple concept, we cannot control the current. VI we can only control. VI minimum देने से ही minimum IB ensured होगा. That is not possible until and unless you choose the base resistance to be maximum as well, because combination of both of this can only ensure the minimum value of the IB. सिर्फ voltage choose करने से नहीं होगा, which is a common, because V equals to IR, the Ohm's law. So for VI to be V high or V max, from the last equation, that is from the equation 6, the condition for maximum value of the base resistance is V high minus VBE sat at the saturation. The base emitter voltage drop is also with certain maximum value, which is IC sat minus HFE RE, that should be equals to V high, that set by your application to application, IB minimum, or HFE into RE. That actually ensures your RB max value. So it is observed in order to maintain a minimum base current, IB minimum, you required in the saturation region of operation, you require a VI to be Vmax and RB must be a non-zero and must be greater than the RB or must be smaller than the RB max. So you have to maintain or you have to choose your RB from this maximum value to ensure the IB to be equals to bare minimum equals to the IB minimum. So those two are very important design rules while we are considering or while we are designing the input voltage as well as the maximum RB. There are certain other specific design rules which we have to definitely to be considered. I am writing one by one those design rules and trying make to understand. The first one, RB is used to control RB is used to control the current in the base circuit for RB equals to sorry for RB equals to 0 but RE not equals to 0, VI is directly appears at the base terminal so that your IE equals to VI minus VBE by RE. If you have to mention your RB equals to 0 and RE not equals to 0, in that case, VI directly appears at the base terminal so that your emitter current will become VI minus VBE by RE. Hence, as per the design, your IE is controlled by the emitter resistance and VI. So while you are designing or when you are controlling the IE, you have to take care of RE, the emitter resistance, as well as the input resistance VI. The second one, the collector current is IC equals to VCC minus VCE minus VI minus VBE by RC from the same. So for VCE equals to 0, for the ideal case, we can write VCC minus VI minus VBE. Please careful, whenever I'm writing this VI, this is small VI because it is an external AC input signal. Others are capital letters because all those are DC sources. RC. So hence IC is controlled by VI only. So this is another controlling parameter or design parameter when we are doing for the IC. There are plenty of other such design rules which design rules we have to uh, which design rules we have to follow in the next class. I will just take leave here, and we will come back with the further design rules in the tomorrow's class. Let's have done your attendance to it. Have to go for the registration. BTech first year. Roll number 1,
Yes, sir.
2,
Present, sir.
3, 4,
Present, sir.
5,
Present, sir.
6,
Present, sir.
7,
Present, sir.
8,
Present, sir.
9, 10,
Present, sir.
11,
Present, sir.
12,
Yes, sir.
13,
Present, sir.
14,
Present, sir.
15,
Present, sir.
16, 17,
Present, sir.
18 present, 19 present, 20,
Present, sir.
21,
Present, sir.
22,
Present, sir.
24, present, 25, 26,
26 present, sir.
27,
Present, sir.
28, present, 29,
28 present, sir.
yeah, 28 present,
29 present, sir.
30,
Present, sir.
31, present, 32, 33 present, 34, present, 35, present, 36, 37, 38,
Present, sir.
39, 40 present, 41, 42, 43,
Present, sir.
44 present, 45 present, 46, 47,
Present, sir.
48,
Present, sir.
49,
Present, sir.
52,
Present, sir.
53, present, 54,
Present, sir.
55,
Present, sir.
Satyajit.
Present, sir.
Thank you. Goodbye.
Sir,
See
3
you.
present, sir. Sir, I have written in chat box, sir.
Pardon me.